Thank you all for joining this evening. I love Docker meetups. I always learn new tricks and tricks and always find out new use cases. I'm going to talk about application of containers to cluster management. Cluster management is kind of hot. We should talk about cluster management using C-Advisor and Kubernetes. There are several other projects that are also looking at this. This is kind of a trend. Before I talk about the application of containers to cluster management, I'm going to start with the history, and how the containers have been there for a long time now, actually. But these disruptive trends are driving containers into prominence. So I'm just going to quickly cover the history and what's happening with cluster management, and in particular Hadoop and Yarn, and why containers are so suitable for this use case. So if you look back, the first implementation of containers was actually done in sometime like 2001. In fact, I did some of the implementation at Columbia University. We did the first research paper on Linux containers that was published in in 2002. So the containers was a concept that we introduced to do these more esoteric things like checkpoint restart, like migration, record, replay. So we viewed containers as a stepping stone to doing these other cool things. But just the containment of applications itself turned out to be immensely valuable, obviously. I don't know what's happening with the sequence. Yeah. So and after the original containers work was done, that was extended to support distributed checkpointing of containers at HP Labs, and this sequence is messed up. I'm sorry about that. And we built a company around it. It was called Meiosis. Basically, we showed containers supporting real enterprise applications like DB2 and Oracle. And that company was acquired by IBM in 2005. So, in the process of the due diligence for the acquisition, we actually showed containers moving back and forth between two completely different hardware, basically using containers to do late migration between two different machines overnight, and we had that robust solution. So, in the first several years, after the concept of Linux containers was introduced, the progress was rather rapid. But after that, not much happened, for many years. So containers have existed for a long time, but then since 2005, no major change. And with these disruptive trends, we're seeing kind of renaissance of container use cases and applying them to these use cases that are emerging now because of these confluence of different trends. So what is happening here? Fundamentally, this is somewhat of a high-level talk initially, but I'll go into the details of the implementation we're doing. But basically, if you think about it, the notion of the computer itself is evolving from a single node to an entire data center. Applications are growing, and the amount of data they're processing cannot fit into one node anyway. So, to accommodate the kind of data, the computer itself is growing into a data center. And when you have the model of the data center being a computer, you also need an operating system to go with it. And there's all these different types of operating systems that are emerging. Kubernetes itself being one of them. Yarn is also kind of fits that model. Mesos is another. And for these types of distributed data center operating systems, the concept of the equivalent of process notion for a single node needs to be built, and containers is kind of turning out to be that central notion of isolation and a unit of compute. For the evolution of operating systems itself, the processes and the way they isolate compute into different applications is central. And that's kind of what containers are doing here in this context. So, I mean, one of the questions that comes up often is, why not virtual machines? Virtual machines have been very successful in the last several years. They've introduced a completely different paradigm of application management, and why don't we use application? But basically, the problem with virtual machines is that there's a fundamental misalignment between application and hardware. What needs to be virtualized, what needs to be managed is the application, but what hypervisor exposes is a hardware interface. So to patch up for that, you need an additional layer of the guest operating system. And in the case of application and the containers, this is much more of a seamless plugin. And in fact, containers are basically just an abstraction. There's no substance behind it in terms of overhead, in terms of the state that they carry. There's nothing there. It's basically lightweight, and it's really an abstraction. And this kind of notion is particularly suitable for data center cluster management because these applications are I/O intensive, and containers don't have really any I/O overhead, and they don't need to boot to instantiate a task, for example. So this happens to be a very nice fit. So now, guest operating system has a problem. So because the underlying interface that a hypervisor provides is that of hardware, guest operating system needs to be used, and that's really a kind of patch. And it has all these issues here. So for example, if you think about a simple event in the application like a write system call, it needs to go through these thick layers of software stack to get to the ongoing resources on the host. The write system call needs to go to the guest file system, which would hand that event to the guest driver, which needs to context switch. And this is a heavier context switch than a typical operating system context switch. It's a VM exit. There's much more state involved in that context switch. And it goes to the virtual device, where the hypervisor does the emulation. There's added overhead, and it sends it down to the image format. There are different types of formats. You can look out to VMDK, OPM, and all those things. They all have their bookkeeping that they need to do, and they add their overhead that gets passed down to the storage protocol and finally to the host. So the problem with the guest is what most of the VM-related innovation is treating. There's entire conferences dedicated to addressing, for example, the problem of VM sprawl, the VM image management, because fundamentally this is a device you don't need the VM image itself is a black box. In order to understand what is inside it, you need to do this parsing, and then you maintain metadata of what is happening. So there's all these so-called innovation that is being driven essentially to patch up the fundamental misalignment between application and the hardware. In the case of using virtual machines for cluster management, first of all, some of these tasks are short-lived, and if the task runs for a minute, and if it takes 30 seconds to boot, the guest operating system, it won't make sense to use it. And if you have this guest operating system, you need to maintain, there's patch maintenance, there's licensing burden, so there's a lot of other overhead that goes with it. And it doesn't scale because it consumes these resources. You might be able to run at most a dozen VMs on a physical host, whereas containers can scale pretty much indefinitely. And of course, you're still limited by the resources used by the application, but containers itself don't impose any additional overhead. And the other problem with VMs is that it obfuscates the underlying network storage and compute topology. You don't know exactly where the resources are. If the application is doing some kind of scheduling, which in this case it is, it won't be able to do the right scheduling, it won't be able to do the right decisions. And you need some kind of mechanism to pass that underlying topology information back to the scheduler. And there's not much opportunity to do any optimizations because the semantics of these application events are lost. A write system call, for example, might be writing to a particular file, but at the level of the hardware, all of that identity to the original event is lost. So all you see is there is a block write to a particular device that won't tell you anything about the semantic context from which that event originated. So there's little room for optimization there. So I'm going to kind of start talking about the use of containers in Yarn, which is basically what we are doing actually at AltaScale. We run a Hadoop as a service. So we have this large one Hadoop cluster, which we call infinite Hadoop, and we are able to partition the resources underlying that cluster to different tenants, each tenant being a customer. And we do that using Docker and containers. And towards that end, we are contributing to Docker and Hadoop projects. Basically, we need right kind of interfaces on both projects and integrate them through an appropriate interlock API. So basically, Hadoop and MapReduce. Hadoop itself is evolving from its core MapReduce roots, and it's actually moved away from being a MapReduce framework to a general cluster management platform which supports a diverse ecosystem of applications and frameworks. For this transition to be successful, you need this isolation, and containers are basically playing that role. So in the case of Yarn, there's these different jobs, and each job is made up of a number of tasks. They all need to run in an identical kind of software context. So we assign a container image to each job, and then basically we run all those jobs, even originating from different customers, on top of the same, on top of shared hardware. So in this particular example, job A has 2 tasks, and they both share the same. So containers provide a number of advantages to Yarn. So first of all, it provides secure multi-tenancy. And one of the things that's actually currently missing in Docker is support for user namespaces, which we've contributed, and we're kind of trying to do that. And we are hoping that those changes get merged. But we have a pilot implementation internally that we are playing with. It does performance isolation, and currently Yarn supports very rudimentary isolation of memory resources alone. And the way it supports memory isolation is also somewhat crude. It basically goes through the process tree in /proc and counts how many pages are being used with this application. That's not the right way to do it. In fact, it should be using at least C groups. But using Docker containers basically goes beyond simple memory isolation. You can basically support any resource that is supported by the underlying C group framework inside the kernel. So we will also be able to drive utilization, because in some cases these workloads are skewed. Some workloads are I/O bound, some are CPU bound, and when a particular job happens to be CPU bound, we run that job on a particular host. Only CPU resources are utilized, and the I/O capacity kind of is idle and left unused. But we're not able to use it because if we compose the tasks of a different customer onto the same hardware, there's security concerns. We can't do that. But with containers, if we are able to isolate those tasks into different containers, then we would be able to more fully utilize the resources of the hardware. So this is a particularly important use case for us. And I already mentioned this before, but basically these distributed tasks, these tasks expect the same environment. The way this is done currently in Yarn is that the administrator would have to go and ensure that all these nodes that are representing this cluster have the same environment, and this needs to be, this is done with Chef and Puppet, but there's still a lot of manual intervention here. But with containers, and especially with the decoupling of the software context from the hardware, the software context required for a particular application sits on the central registry, and it gets pulled on demand. So basically, it is guaranteed that all the tasks of an application run in the same software environment. Once again, right, the cluster might be running applications, applications from different jobs, and when they run on the same hardware, they could have particular software dependencies. A particular job might have a version dependency on R, and a different job might require R as well, but a different version. So when these tasks need to run on the same host, you need to make sure that those dependencies don't conflict with each other. And there's no easy way to do this actually in current yarn. Clearly, if you use containers and you have a private mount, you won't have those dependency conflicts. And basically, if the software context required for these applications can be programmatically generated, that makes life a lot easier, and Docker files provide that approach. So if the version number for a particular application needs to be upgraded, it's a simple change to the Docker file, and then you rebuild the container image, upload it to registry, and the new version gets built. So these are the most common Docker use cases, but they provide immense value in the context of yarn. So I was mentioning about UID virtualization earlier. The different namespaces that back a container have been around in the kernel for a long time. I mean, the first PID namespace was introduced in maybe early 2.6 versions of Linux. But since then, there have been many namespaces that slowly made their way. But the most recent one, as of several weeks ago, is UID namespaces. And this is crucial to provide security isolation between containers running on the same host. And this has been a problem with Docker now. I mean, if you go to some of these meetups, you hear that even though you have a regular user on the host, you just do Docker run something and then you suddenly become root. Although that's not completely true, but basically user namespaces would avoid those kinds of security issues. So now the root in the container is mapped to a regular user on the host. What this allows is the application can basically do anything the root does inside the container, but then the scope of the privilege is limited to the container itself. So there's wide latitude on what the application can do, but you won't be able to impact other containers running on the host or the host itself. The actual semantics of user namespaces is very complicated. Basically, it allows arbitrary mapping of UIDs within the container to UIDs on the host. But the most crucial piece of this function is remapping root in the container to a regular host. So this will be the first piece of support that we will be supporting in Docker. So I've been conservative, and I have this is a good point to stop, but if I have time, there's more backup slides that I can go into. I think I do have time. So there's a number of references here. I will probably upload these slides somewhere, but basically these references point to different Docker tickets and the tickets on the Hadoop side as well. So you can follow through, and if some of this interests you, please contribute. So before we started doing this work, we needed to make these changes, and making code changes and then working with the community to get those changes into the mainline distributions is not easy. So we need a way to immediately use these features. So the value is clear, but we needed to move forward quickly. So we have this dichotomy. Should we run containers on top of Hadoop, or should we run Hadoop on top of containers? Basically what we're doing right now is basically running Hadoop on top of containers. Container represents it provides a consistent host software environment, and Hadoop already runs on top of these machines. So as long as I make containers look somewhat similar to the host, then I should be able to run Hadoop directly on containers, and that in fact addresses most of the use cases in the case of yarn. So this is kind of what we initially were doing. So we had we basically dedicated completely distinct hardware per tenant. Security is obviously very important, so this is awesomely secure. There's no sharing of resources, and every customer gets a completely dedicated cluster. This works well, except we could not scale the business this way. There's a lot of wasted resources here. So in this, each horizontal strip represents one physical machine, and then basically 3 units of resources. And all the greater portions are unused. So utilization is a problem, and also we have the same problem with software dependencies. Customers require different types of software, and we would have a base platform that we maintain, and every time there's a new request, we have to go back and change our base platform, even though not all customers require that. And that's a very unscalable approach. So what we have done initially is simply introduce containers. Basically, we're running all compute, all workloads inside containers. Initially, they're static here, so each of those machines is running 3 containers in this illustration. And just the fact of running workloads inside containers gives us that decoupling between hardware and software. So now we can map each customer to a particular container image, and we would then be able to change the software context for different customers individually. So we don't have to change our base platform, which is a much larger maintenance burden. And once we have that, now we can pack those containers more densely. So in this example here, all these gray red portions represent unused parts of the resources on those machines. Basically, we will take them and then compose them onto fewer nodes. So we're packing them closely together so that frees up these nodes, we can power them down. So basically, we're driving utilization. And also, we can use existing features of Docker's resource limits. So it currently supports CPU and memory, which are really the core for these kinds of workloads. That works well for us. So we can shrink. So now these containers are basically fungible. We can take away resources from one container or one customer and then assign to other. Not quite on the fly, but that would be desirable. That would be nice to do. We have to get that to flag that work, but at least when we create the task, we'll be able to say what kind of resources of the host should be added to the container. And the same co-scheduling of compute and storage resources is also possible in this case. So customer 1 is mostly storage bound jobs, and the CPU resources of that node can be assigned to a different customer by providing right isolation through containers. So this is the charts I have. I'd be happy to take any questions.
I was wondering, like, it makes a lot of sense for you, like, Hadoop, providing Hadoop as a service, because you need to support multi-tenancy and all, so it makes a lot of sense to have, containers using Yarn, using containers. Do you think it's applicable to non-multi-tenant, generally use cases in general? Like, if there is no multi-tenant requirement, let's say, in that case, do you still think that is an advantage because you probably there is still a little bit of overhead here, right? Compared to, let's say, the current native Yarn implementation, just using processes.
Actually, especially for Hadoop workloads, there is more overhead. If you look at container and the jobs that get run in Yarn, these are mostly IO-bound, IO-intensive type jobs. and for them there is
No, it's like
no-
executing a process versus you still go through a little bit of overhead. I don't know, it might be minimal, but still there will be some overhead because you're bringing another layer.
There's no runtime overhead. There's definitely no runtime overhead. Unless you're running some kind of micro benchmark, for example, if you're doing get PID in a type loop, then you will see some overhead. I mean, we did a lot of extensive measurements on containers. I mean, this is back from 2002, right? So there's a paper that we wrote comparing containers versus VMware's implementation at that time. So basically, there's no overhead. But these kinds of workloads, overhead is less than noise.
And the other advantages, probably you mentioned a couple of other
So
advantages.
there's a number of other advantages.
Yeah, but there one advantage is that is like you can balance the IO bound jobs and CPU bound. But then, how do you give the hint to like how do you schedule those things? How do you know that this is IO bound versus CPU bound? So somebody has to interpret. Yard doesn't know it's IO bound or CPU bound. So somebody else has to give a hint that okay, co-locate them because this job is IO bound and these two.
So there are general patterns. There are general patterns, and they can be deduced also by looking at logs. And there's a different area of work that
some other framework has to make
yeah.
it
So
better than.
you kind of know, right? I mean, for example, Terragen is completely IO bound.
Yeah.
And based on the complexity of your regular expression, you would know whether it's compute bound or CPU bound. So there's heuristics, there's bodies of work that tell you what kind of job it could be, even based on historic patterns. And basically, containers provides you the ability to use those resources. In the absence of containers, you can't even do that. Even if you know what kind of job it is, you can't compose them together because of security reasons. So basically, containers, this kind of virtualization allows you to do that.
One more is like, okay, so you are taking care of processing aspect of Hadoop, but there are still other things like HDFS, and then there is catalog, all those things you still need to take care in multi-tenant. So that's separate. How do you handle multi-tenancy, those things, and combining that thing?
There are problems, right? So there are general problems. There are general problems in yarn. Containers actually do solve a number of core problems, but obviously there are some outside the scope of containers. Management is generally a problem. Containers does make that significantly simple. It's not a magic bullet.
Okay, thanks.
So that was an interesting talk. So with regard to running Hadoop on containers, now you're talking about different containers for different customers, different sets of containers. Now, typically when you have a cluster, you would have the node manager and the data node and so on, these kind of services. Are those getting shared across those containers when you're running multiple containers on a host?
So the way there's different models of doing this. The initial model we are using in our pilot is we share the resources, but we still keep the main node and the HDFS file namespace distinct between tenants. But it's possible. You can kind of conceive of a chroot type notion for HDFS as well. So you would run. It is possible to run just one instance of main node, and then provide a kind of chroot for different tenants, and then provide isolation at the level of main node itself. But that requires some changes to the code, changes to yarn code. Some of that, we'll do because that's nice to do. But for now, we have distinct name nodes for different customers.
So each of your containers has got its own name node?
Each container cluster has its own name node.
Right. I mean, sharing the name nodes certainly would have more efficiencies rather than having multiple name nodes across these different containerized clusters.
It depends also, right? So the customer might not want to share the same JVM and the same processes with a different tenant unless it is proven secure. And obviously that requires core changes, first of all. And then there might even be some compromise in terms of transparency because I might not be able to look at the entire namespace of HTTPS file system because some of it is forbidden for me because that belongs to a different tenant, and that might not be acceptable.
Yeah, and on the other hand, I mean, you might say that you might, in a company, you have different departments and actually want to share that data and you want to have
Absolutely,
data
that's,
as well.
yeah.
I think I can see
Yeah,
your
that can be
point.
done. So sharing is important as well, and we can address that by doing remote node.
Yeah, and this namespaces is one aspect. What about the node manager and so on? Are those separate as well for containers?
Yes, yes.
Or-
So
or
we
actually-
kind of have a completely disjoint set of containers for each customer cluster at this point.
I see.
And then we are doing work with Yarn, like I showed, where we would run one cluster, and the node manager will spawn containers per task. And the node manager will be able to spawn containers for tasks representing different customers. And do write isolation. So we have an initial patch to Yarn to do that.
I see. So Yarn already has support for C groups and so on internally.
Yarn
I mean-
quite doesn't, it doesn't use, there's an open ticket, it's not merged.
No, right now it has resource, I mean, it
does-
allows you to,
Yeah, it doesn't use, there is support for memory isolation, and it is done, like I said, using, basically doing manual accounting of
well,
process
it
usage.
does run in C groups and it does give you, separate.
It's not merged, it doesn't do that. I mean, there's work in progress, but it's not, it doesn't do that currently.
Okay. And how much is the performance overhead of your solution there? I mean, by going with containers and so on, have you actually estimated it?
Yeah. So there's extensive work done on comparing performance of containers versus native versus VMs. At runtime, there's no overhead. You might see some numbers, but I mean, basically those are completely unrealistic scenarios, handcrafted specifically to pound down, those control paths which do the interception and isolation. Basically, otherwise there's no overhead for real applications. But then there is overhead that comes from the big movement required for bringing down container images. So that's there, and that's much smaller than moving around VM images, because here you're dealing with deltas, because basically these containers are not opaque like VM images. So you know what actually is made of. You know the constituents of this image.
So this is documented, I mean, this information is available, the performance experiments that you have done?
There's hundreds of papers. Yeah. This is available.
Okay, thanks.
So what ultimately made you decide to go down the route of implementing Docker and Yarn directly instead of looking at alternative clustering, cluster scheduling tools like Mesos, who has equivalent projects for integrating Docker? And what made you choose to go the route of integrating Yarn directly, and what do you see as the potential benefits of it?
So is the question comparing Yarn versus Mesos?
Yeah, basically, why did you decide to...
So why don't we just use Mesos, which already has some kind of integration with Docker, and why do this for Yarn?
Yeah.
Well, Yarn is the kind of the mainstream Hadoop, right? Word cloud era, that part. Basically, that's the Hadoop distribution, and it has a number of problems currently, and they can be effectively addressed with Docker. Mesos actually, it's a different approach. It's not built for MapReduce. It is at least it is relatively newer in terms of there's Mesosphere funding that work right now, but it is relatively new. There are some anyway. I don't want to go into the comparison between Yarn and Mesos, but containers provide a lot of value to Yarn.
Right. Quick question, right? I'm still trying to kind of understand why Hadoop on containers is a special case or why it has some special significance. Do you see any special challenges on deploying Hadoop on containers because of which you have to go through some hoops here, or what is so special about it? Like if you take any other MPP application, right? Assuming each container is like a small box, right? Then can't I just deploy any Hadoop deployment similarly on top of containers, assuming each container is a different VM or a box, right? So why is this something special? I'm missing it.
Well, you kind of need to, I mean, at a conceptual, theoretical level, a container basically looks to you like any other machine. You can SSH into it, do what you do on a physical machine that works. But when you actually have to run this in production, there's a number of issues to be addressed. Like I was telling the UID namespaces, for example, that's an additional feature that we needed to put into Docker to use it. For VMs, you might not need that.
Probably that is something because, okay, you are a as a service company where multi-tenancy and the security has to be really rock solid, right? If I am in a trusted environment within a data center, probably that may not be as significant as a right?
There are actually core issues as well. You basically want to look at this application as a cohesive unit consisting of these distributed set of tasks. And they all need to kind of work together. So when you, for example, create HDFS user on these machines, it needs to be available, and so I mean, most of these issues kind of boil down to the distributedness of this application. So you need to make sure that, for example, these containers need to be put onto the network, to the right network. If I need to do isolation at the traffic level, then I need to make sure that there is a one-to-one mapping between the tasks of this application and the subnet items, and creation and deletion of UIDs. So any distributed resource used by the application needs to be arbitrated correctly.
I think, okay, just to kind of crystallize the question, right? Okay, in my Hadoop, for example, current setup, I have 5 data nodes running on 5 different boxes. If I just move this 5 data nodes into 5 containers, is there a big problem in that?
The support for resources inside containers is complete. It's fairly complete at this point. So, I mean, earlier, even a year ago or so, for example, /proc did not have the right entries, so some of these applications would stumble on that. Basically, the interfaces that the host operating system exposes are not fully transferable within containers. But at this point, based on our experience with running these applications, it's complete. So there's no theoretical issues. But when we're doing operations, obviously you're going to all these issues. Nasser is here, he leads our operations for container use and basically we run these applications on a daily basis. So getting this to run in production is a challenge.